Welcome. This TDI CAD-cast will cover liquid and gas flow simulations through pumps and valves. My name is Enrique Garcia. So, SolidWorks offers a full range of design validation tools to address all kinds of analysis needs, including mechanical design validation, motion simulation, and computational fluid dynamics. Our mechanical design validation tool is an FEA-based design validation tool that helps in studying failures due to stress, excessive deformation, and will also do factor of safety checks. SolidWorks Motion Simulation is a physics-based motion simulator providing analysis of moving components. This facilitates designs of motors, actuators, gears, and cams. Motion can also help reverse engineer and perform interference checks. SolidWorks Flow Simulation studies the flow of any kind of fluid inside or outside of the product. Examples include pumps, valves, electric enclosures, and medical and drug delivery equipment. All three of these products are fully integrated within SolidWorks. Results from SolidWorks Motion and SolidWorks Flow Simulation can seamlessly be used with our mechanical design validation tool, SolidWorks Simulation. So today we're going to be focusing on our CFD product, SolidWorks Flow Simulation. Like I mentioned earlier, SolidWorks Simulation focuses on fluid characteristics inside or outside of your SolidWorks products. More specifically, we can simulate liquids or gases through and around these SolidWorks parts and assemblies. In the following examples, we're going to go in and understand pressure drop with a specific assembly. We're going to also look at velocity profiles, and potentially we could look at heat transfer characteristics in your design. For our second example, we're going to simulate rotational flow of a pump and generate data so that we can go in and create pump curves. Now with SolidWorks Flow Simulation, as with our other analysis tools, we don't have the need to go in and export, patch, and repair imported geometry. Everything works seamlessly within SolidWorks. There's no need to go in and create a separate model to use for production. There is no need to import or export geometry. We can simply go in and use the same SolidWorks model we've been using in production for our analysis. The great benefit for this is that if you need to change your design on the fly, you can do so, come back to your SolidWorks simulation, and perform an updated simulation on the new geometry. And as with all of our other products, we have the same property manager interface that you see inside of SolidWorks. So if you're comfortable using our SolidWorks tool sets, you'll definitely be comfortable using simulation as well. For our first example, we're going to be focusing on flow through a ball valve assembly. Now there are certain questions you may ask when it comes to designing a successful ball valve. Some of them may include, is there an even amount of flow through both outlets? How will the angle of the ball valve affect the flow rates and flow characteristics of my piping in my assembly? Or how will the outlet flow rates vary with changing of the inlet flow rates? Also, pressure drop is pretty important when it comes to designing ball valves and piping systems. So we're going to also take a look at pressure drops and pressure characteristics throughout our design. Let's open up SolidWorks and take a look at our ball valve assembly. To be able to interrogate the model more efficiently, I'm going to go in and perform a section view of the model, cross-sectioning and removing half of the design so we can explore the internals more efficiently. We're going to be creating a flow analysis with my ball valve partially opened so we can take a look at the flow characteristics of pressure and velocity throughout the internal volume of my assembly. Let's begin a new project, and let's go in and designate standard units. For analysis type, we're interested in the internal volume of the geometry, so we'll choose internal for the analysis type. The fluid we're going to be using here is going to be water, so let's go in and expand liquids, and let's choose water. Let's accept the default wall conditions and the default initial conditions for standard temperature and pressure. The last portion of this initial setup wizard will help you indicate a global size for your mesh or sampling of your design for the analysis. The higher the value, the more points of calculation are required to solve the study, increasing the accuracy of your study, but also increasing the amount of resources and time needed to create the calculation. I'm going to go ahead and stick with the defaults for now. After we hit finish, you'll notice that we have a new interface to the left of our graphics area. The first folder in the input data directory is the computational domain folder. This designates the size of our computational area or volume that we're going to be solving in. We're currently interested in applying conditions for introducing fluid through the entrance of our system and conditions for how fluid will exit both ends of our system for our study. We do these with boundary conditions. To apply an inlet boundary condition, we're simply going to select in the folder and choose the inlet face of our system. We're going to specify a mass flow of 1 kilogram per second. Flow simulation will display symbols corresponding to faces or any reference that may have a condition so that you can keep track of all the different conditions and input boundaries you've applied to your study setup. Now that we've applied an input boundary condition, let us apply an exit boundary condition on the opposite end. Under the type section of boundary conditions, I'm going to choose the pressure openings, and we're going to introduce the exit points of this assembly to the environment. We're going to be specifying environmental pressure. If you would like to override this at any point, you can do so under the thermodynamic parameters section in the property manager. And at this point, our flow simulation setup is complete. We've established the input parameters and our exit parameters in our system. Let's continue to the next step and let's run the analysis. Now the flow simulation solver is pretty unique in the fact that it allows you to go in and commandeer additional computers on the network to help run more involved flow simulation studies. We also have the ability to go in and select how many cores or CPUs we can use for this particular calculation. Perhaps you're given the situation where you need to continue to work on additional projects on another software on the machine. You can use perhaps half of your cores and still be able to have enough resources to continue working while you're solving your study. You'll have the ball valve or the actual solver project window pop up. At this point, we can go in and take a look at a preview of what's happening as far as solving and converging our results for our study. If you see that your pressure or velocities, whatever you're previewing looks incorrect, you can stop your calculation prematurely to save calculation time, revisit your study setup and assumption so that you may rerun your study to completion. Once the solver is finished running, we can close the solver window and our results will be loaded under the results folder to the left of the graphics area. Now, if we were designing this particular ball valve assembly, we would be interested in the pressure and velocity profiles within and around the ball valves. So let's go ahead and take a look at those results. I'm going to cross-section using the same plane I used to create the section view, and I'm going to specify the pressure parameter. Now once I hit my preview, I can take a look at my pressure distribution from input to output. If I agree with the visual representation of the results, I can click the OK button. Otherwise, I can go ahead and add perhaps more detail and perhaps show display vectors to my results as well. In this particular results plot, I can see my established pressure gradient as well as the direction vectors of my pressure. This allows me to get more detail and more information off of my result plots. If you notice to the right of my screen, my pressure normalizes as we head to our exit points. But if I zoom into certain areas of interest, you'll notice that we have a recirculation of the direction of my fluid as the liquid exits the ball valve. And also we notice some recirculation on the lower side of my exit point. Now that we've gone in and analyzed the pressure distribution, let's take a look at the velocity profiles throughout the length of our design. Looking at our velocity profiles, we can definitely see that this is going to be an asymmetric result, and we have a higher velocity in our upper exit portion of our piping system than my lower portion of the piping system. We could perhaps deduce that this could be due to the recirculation effect that's occurring here and also to the left due to the partially opened ball valve. To examine this further, we can go ahead and introduce flow trajectories in our system so we can characterize our flow fields using a better visual, and will provide better animation in our study results. For this, I'm going to activate the flow trajectories capability, and I'm going to select the inlet and outlet points of my study setup. After specifying velocity for a result type, we can see here a more illustrated look to our flow fields. Now, depending on the result type that you'd like to show, we can switch the result type or characteristic to other types of shapes. For example, we can go from pipes, or maybe we can go to arrows. Anything that will make illustrating my results more realistic or more intuitive to your viewers. So now that we've gone in and we've taken a look at the amount of flow through both outlets, we've also taken a look at the pressure drop. Let's see how the angle of the bulb will affect the flow rates and our pressure results. For this, I'm going to go in and alter the angle of the ball valve. Because we're fully integrated within SolidWorks, there is no need to go in and recreate the setup or import and export any geometry. All that is needed is to go in and rerun your flow study. Now again, if your preview results look incorrect, this would be the ideal time to stop your study, reassess your initial setup or assumptions, and then return to running your study. Now once the solver is finished, we can go back to our flow interface, and our current results will be updated and ready to be displayed. Now that we've finished running the flow simulation study for the updated model, let's take a look at our pressure profiles and velocity profiles. Simply go back to your results folder and re-show the cut plot. We should now see a nice symmetric result with regards to velocity profiles. If we switch this from velocity to pressure, again we can see a nice symmetric characteristic between the opening, between the inlet and outlet portions of the ball valve, as well as the rest of the design. In addition, we can get some quantitative data with regards to velocities and pressures. We can interrogate individual surfaces and get any kind of information you see under the parameters section in the Property Manager. In addition to qualitative data, we can also get quantitative information by using surface parameters. This will give us information about a specific surface within our study. We can also use point parameters, which will give us information on a specific node of calculation within our whole computational domain. And lastly, we can use XY plots. XY plots will allow us to take a sketch entity within the computational domain and allow us to sample and plot our data within a graph. Let's take a look at our velocity profiles as we go from inlet point to outlet point on each of these outlet points. For this, I'm going to choose a sketch representing outlet 1 and a sketch representing outlet 2. Next, let's choose the parameter we want to take a look at more closely. Once we hit the Show button, we can see a little graph at the bottom. More importantly, we can export these results to Excel so that we may interrogate more closely. Since our results for this velocity profile are are quite symmetrical, we can see that verified within our XY plot. The blue plot representing outlet 1, which is the top exit, the red plot representing outlet 2, which is our bottom exit. For our second example, we're going to talk about how to simulate flow through a pump design. Presented are some of the most common questions you may ask whenever you're in charge of designing a pump, such as what is the head or the pump head at different flow rates? Which flow rate gives us the maximum pump efficiency? How will our blade designs affect our flow fields, and the efficiency? All of these questions can be sought after and visualized through SolidWorks Flow Simulation. Let's open up our SolidWorks Flow Simulation and take a look at the model you see to the left of your screen. Now for this particular example, due to the time requirement of this particular study, we're going to go in and step through the setup of our flow simulation study, and we'll take a look at the already calculated results. Now with our first example, we went in and satisfied all of our initial mesh analysis type. We can get access to all that information after our initial setup quite easily. To review my setup, our analysis type is an internal analysis. We're currently interested in what's going on the inside of this particular assembly. We've also specified gravity, a gravitational pull in the positive z direction. And we've also taken into account rotation. In our flow simulation study, we are assuming that the blades are going to be affecting the flow fields, hence we need to take into account rotation. Our fluid type, we're going to be using water. Default wall conditions. And default temperature and pressure constraints. As we mentioned, we're wanting to see what the flow fields and the flow effects look like as a result of the impeller rotating at a certain velocity. This can be specified to the left of the graphics area. At this rate, we're taking that particular impeller and we're revving it at 1200 RPMs. We're also introducing our fluid medium into our system from the bottom of my screen there at 500 gallons per minute, and we're opening the other end of the system to the environment at standard pressure and temperature. Now, in this particular example, we're interested in specific points of interest. For example, the inlet and outlet pressures that we can use to calculate the head curves and also later calculate efficiencies in our model. And we're also interested in the corresponding inlet and outlet volume flow rates. We can specify these individually within the goals section simply by selecting the particular face you're interested in and filling out the parameters box. After our flow analysis is already set up, we can look at our results. Perhaps we're interested in the velocity gradient throughout a section of this particular volume domain. Let's go ahead and show our first cut plot, which demonstrates the velocity profile. With our vectors turned on, we can definitely see that we're having our fluid medium being sucked through our inlet, being rotated and agitated about due to the impeller, and being exited through the top portion. Such as before, we can alternate the metric we're using, and let's switch this over to pressure. And let's take a look at the pressure gradient throughout our flow fields on our design. Looking at cross sections of our design can only get you so much. Let's go ahead and show flow trajectories. For a flow trajectory, we're going to go in and look at the velocity characteristic within the internal volume of the model. As you can see, we can get quite a bit of detail with these flow trajectories. Next, let's visualize our flow fields with arrows and an animation with flow trajectories. This can help visualize in greater detail what's going on internally within our flow fields. This is all good data, but what about quantitative data? We're currently interested in looking at inlet and outlet pressures, volume flow rates. We can get access to all of those required values by using the goal plots. During my study setup, I specified certain values that I wanted highlighted by the software, with our goal plot we can call upon those values and display them. With this calculated data, I can now begin to construct some pump curves that will be able to characterize my pump design. Going back to our presentation, now we can play with the flow rates to go in and look for the maximum efficiency. We can also play with the rotational velocity, and because we are operating within the SolidWorks infrastructure, we can go in and change our blade designs, rerun our study, without having to recreate our setup and determine how these blade designs affect the flow fields. And as we alter our flow rates inside of our study setup, rerun the study, we can calculate information for head and efficiencies and get points for those and start plotting those to characterize our pumps. And this is pump design with flow simulation. So how is pump analysis done now without flow simulation or any simulation product or tool? This requires you to create perhaps a see-through rendition or prototype of your pump design and piping system, inserting certain dies or markers inside of your flow fields, purchasing and installing flow sensors and pressure sensors, temperature sensors perhaps, ultimately costing you significant time and money. When you run through that workflow within a virtual landscape, such as SolidWorks Flow Simulation, you can save yourself significant time and money to perform the same functions. So where does flow simulation fit in amongst the other simulation packages we offer with SolidWorks? Flow simulation can be purchased as a separate license, apart from our simulation FEA analysis packages. If you're an individual user and have a standalone seat, you would just purchase the flow simulation software, update your install, and you're good to go. If you're on a shared network, you would incorporate the extra seat or extra license of flow simulation on your network, update your client installs, and you're also good to go. There is no need to uninstall everything and reinstall everything, just to include the extra added functionality of flow simulation. Additionally, here's a small list of successful companies which currently use SolidWorks Flow Simulation. If you're interested in learning more about SolidWorks Flow Simulation or any of our SolidWorks products, please contact your local reseller or contact us, Digital Dimensions, at www.ddicad.com.